The universe is full of amazing and awe-inspiring events. Of course, there are the ever-familiar black holes, whose mysterious nature we marvel at, and the brightest objects in our night sky, supernovas.
But have you ever wondered where they came from? Interesting enough, their origins lie within a special type of star, called a neutron star, and its many variations, like pulsars and magnetars. The consequences of these neutron stars can be intriguing but harmless phenomenon.
While others could literally change life as we know it. Before explaining how certain neutron stars could literally obliterate everything we know and love, I'll explain a little bit about how they work. First of all, neutron stars form from one of the two primary star categories called population 1 stars, like our sun. However, even though the sun is a population 1 star, the other qualification for the formation of a neutron star is the mass of the star. Only those stars that are between 8 and 20 times the mass of our own sun are eligible to form a neutron star upon their deaths in a type 2 supernova. To put this into perspective, if the sun were the mass and density of a basketball, then for a type 2 supernova to occur, the star in question must at least be the mass of a cantaloupe, but no greater than the mass of a watermelon. The iron core of a massive star remaining after the star death is about 1.5 to 3 times as massive as our sun, and is surrounded by the stellar debris of its previous layers blown off by the supernova. The combined mass of this debris increases the massive amount of gravity exerted on the iron core. At a certain point, the gravitational forces become too large, and the star collapses and melts the protons and electrons that have been opposing the collapse into neutrons, thus creating a neutron star. Now that we know how neutron stars form, we can delve into what they are. They are extremely dense objects, only about 12 miles in diameter, but still containing up to 3 times the mass of the sun. Therefore, a teaspoonful of delicious neutron star would only weigh about, a billion tons.
Pulsars, also known as pulsating radio stars, are neutron stars that emit radiation. They're highly magnetized and they rotate. They were discovered by witnessing radio sources that blink at a constant frequency.
Pulsars have a rotational magnetic axis at different locations, similar to Earth. This is why the beam of light from the magnetic axis appear to sweep around the rotation of a pulsar.
So it's kind of like a lighthouse, and it's flashing beacon to a ship too close to shore.
Right. The first pulsar witnessed is located in the Crab Nebula. The Crab pulsar rotates 30 times a second, emitting a double pulse in each rotation. In addition, some pulsars emit X-rays. At times, this makes them easier to spot. Since the first discovery, scientists have discovered over 1,500 pulsars.
Another unique trait that pulsars have is their incredible speed. They would move so quickly it would only take them 16 seconds to travel from London, England to Sydney, Australia.
That's pretty crazy. There are no pulsars orbiting in unison with our sun because our sun is a lone rider in our solar system. But there are many pulsars that are discovered in binary systems. Normal stars, white dwarfs, neutron stars, and planets are just some of the interstellar objects that accompany pulsars in orbit.
Will our sun ever become a pulsar?
Unfortunately, our sun will never become a pulsar due to its small size, but the more massive stars are fated to end their lives as pulsars.
Another consequence of neutron stars are quasars. When neutron stars die, they create supermassive black holes. Quasars are the objects in the family of active galactic nuclei that these supermassive black holes generate.
First classified as quasi-stellar radio sources due to the radio waves they emit, quasars are the light from particles racing from the edges of supermassive black holes in the center of a galaxy at nearly light speed. Material around a supermassive black hole forms an incredibly hot accretion disk that emits an enormous amount of radiation. This creates a magnetic environment that produces twin jets of material that courses into space for millions of light years.
Quasars are the brightest objects in the universe and emit massive amounts of energy, more than 100 normal galaxies combined.
So does that mean there could be a quasar in our own galaxy?
Many scientists agree the Milky Way could have produced a quasar in the past, since we have a supermassive black hole at our center. However, currently no material is close enough to form an active galactic nucleus.
Someday, if we collide with other galaxies, the supermassive black hole at the center of our own galaxy may be able to create a quasar once again.
So what were you saying earlier about how neutron stars could cause mass destruction to life on Earth?
Well, I was referring to a specific kind of pulsar called a magnetar. These special pulsars have a stronger magnetic field, rotate slower, and have much higher energy gamma radiation bursts than normal pulsars. Magnetars were discovered when an abnormally large gamma radiation burst hit several spacecraft in the solar system, but the idea of the magnetar wasn't proposed until several decades later.
It's estimated that only 1 out of every 10 supernovas that doesn't form a black hole forms a magnetar instead of a normal pulsar.
Why are they so rare?
Well, you see, they require very specific conditions to form, similar to the Goldilocks zone that Earth resides in. As a neutron star settles into its equilibrium, the proton superconducting liquid creates a magnetohydrodynamic dynamo, which paired with the slow spin of the still-forming star creates an incredibly strong magnetic field.
The active life of a magnetar is relatively short. It's only about 10,000 years, but incredibly violent.
How violent is it?
Well, if I had to choose between living near a magnetar and a black hole, I'd choose a black hole every time.
The magnetic fields of these celestial objects are between 10 to the 8th and 10 to the 11th Tesla, which is hundreds of millions of times stronger than the strongest man-made magnet, and is quadrillions of times stronger than Earth's own magnetic field. If one of these came close to Earth, it would have catastrophic effects. If a magnetar journeyed towards Earth and was the distance from halfway from here to the moon, it would wipe all of the information off of the magnetic strip of credit cards. If a magnetar was only 10,000 kilometers away, if you had braces, you could get pulled off the face of the Earth. If a magnetar was a mere 1,000 kilometers away, it would cause all life to cease. The magnetic field would be so strong it would distort the electron clouds of atoms so much that the chemistry of life would no longer be possible. Magnetars don't necessarily have to be close to Earth to hurt us. If the gamma ray blast from a massive starquake that reached us in 2004 from a magnetar that resides 50,000 light years away happened within 10 light years of Earth, it could have caused a mass extinction. You probably should be more worried about your finals than the effect of a magnetar. But if one did come close, it might be a good idea to tell your orthodontist. Well, that's all the time we have for today. Thanks for watching this episode of Origins of Everything.
There's a starman waiting in the sky. He'd like to come and meet us, but he thinks